Hi, everyone, and welcome back to Rosie STEM. I'm Amanda Jotty, and today we're going to be doing some examples of how to calculate a bootstrap confidence interval in Python. So let's get right to it. All right, so here's my Jupyter notebook. If you're not familiar with how to use a Jupyter notebook, I will link my video on how to use them right here. The first thing I do is always import the libraries that I need. I don't need any special libraries to do a Bootstrap confidence interval. I just need pandas and NumPy, and I imported matplotlib as well here. I'm going to use some data called the penguins data. It's a very commonly used data set on penguins in Antarctica. So it has the species of penguin, the island they live on, as well as some metrics about them and their sex. And what I want to know is how much bigger are male penguins than female penguins. So let's look at the difference in average body mass. So average body mass here in grams. So my statistic, like my point estimate, is going to be the average of the male penguin body mass minus the average of the female penguin body mass. If you're not familiar with this little forward slash here, it just allows me to put code on multiple lines instead of just one. So the difference is 683.4 grams. So the male penguins are 683 grams heavier than the female penguins on average. This is our point estimate. And what we could do is just report that and say, this is my point estimate. This is probably close to the parameter in the population of all penguins. But it's useful instead of just giving one value to kind of give a range that we think our parameter is going to be in. And that range comes from calculating our 95% basic bootstrap confidence interval. So here is an image that reminds us of the bootstrap process. If you haven't seen my video on the theory behind bootstrap confidence intervals, I'm going to go ahead and link that here. It might be useful to go through that, and then you can come back to this video. But what we're doing is we're going to treat our sample of penguins like it's the entire population of penguins. And we're going to treat our point estimate, this 683 grams, as if it's our actual parameter, right? So we're going to call that our theta B. And we're going to take samples from our sample and calculate new bootstrap statistics on each of those samples. And these bootstrap samples that we're taking from our original sample are all going to be taken with replacement. Sampling with replacement allows us to make sure that we're getting some sampling variability in each of our samples. Otherwise, we're going to end up getting the same sample over and over. So first, I need to know what my sample size is going to be. So I look for what n is going to be. This is the number of penguins that I have in my sample. And then to take a bootstrap sample from penguins, I can use pandas.sample method. And what that does is it will randomly sample rows from the penguins data frame. And I've told it to randomly sample n rows. So n is the number of rows in penguins. So it's going to be the same size as our penguins data frame, but because I've set replace equal to true, I'm not going to get the exact same sample. I can maybe sample the same row multiple times, and some rows might not get sampled at all. And then once I have my bootstrap sample, I can calculate a bootstrap statistic on that sample. So here I'm doing the same thing that I had done overall for my full sample to find my point estimate, but now instead of doing it on penguins, I'm doing it on penguin boot. So I'm doing it on my bootstrap sample. And you can see that the difference between male and female penguins that I get here is pretty close to the 683 that we have as our point estimate, but there is a little bit of variability, right? It's a little bit smaller, so 672 grams this time. And what we want to do is not do that one time, but do that a lot of times so that we can get a whole distribution of what these statistics look like. So here I've got an array where I'm going to save all of the Bootstrap statistics that I calculate. And then I have a for loop that is going to execute this code 1,000 times. Inside my for loop, the first thing I do is get my Bootstrap sample. So this is the same code that we used up here to get a single Bootstrap sample. Once I have that sample, I need to calculate my statistic. Again, same as what I did up here, but I'm now saving it into a variable name. I'm going to call it stat. That way I can save it to my empty array up here. So I'm just going to keep appending that to my array, and then I'm going to have an array of 1,000 Bootstrap statistics based on my 1,000 Bootstrap samples that I'm taking. Then I just use matplotlib's pyplot to make a histogram. So I just did plot.hist, bootstats, and I'm making a very simple histogram here. I don't really have any labels or anything, but this is frequency on the y-axis, and my statistic values, my Bootstrap statistic values, are on my x-axis. And you can see it's relatively normally distributed, right? Unimodal, symmetric. And I also have put this dot here using dot scatter. And this is where my point estimate was. So this is my statistic from my original sample from that penguins data set. And you can see that they're all centered around that original sample statistic, which makes sense, right? That's what we're gathering data from. And we can kind of see how far away to either side these statistics tend to get. So how much smaller and how much larger than our point estimate do we tend to be on average? So this is my Bootstrap sampling distribution of the difference in body mass between male and female penguins. The first thing I notice is that this never crosses 0, right? So it looks like every single statistic I got showed that male penguins were heavier than female penguins. Now, if you remember back to this here, the sampling distribution that we want to be able to calculate our upper and lower bounds for our confidence interval is actually not the sampling distribution of our Bootstrap samples. It's the sampling distribution of the difference between our Bootstrap samples and our Bootstrap parameter, right? Our original statistic, but that's what we're treating as our parameter here. So this is going to kind of tell us on average how far away are our statistics from our point estimate, okay? So here, I'm going to take my Bootstrap statistics. I'm going to subtract my Bootstrap parameter, right? My statistic from my original sample. And you can see it's a very similar distribution, right? It's the same. All we did was shift it, right? We just shifted it to the left some so that now it's centered at 0. And we can see how far away to either side it tends to be on average. How wide is our distribution versus it being skinny, right? What's the variation? So we want a 95% confidence interval. 95% means that we need to look for the middle 95%. Where is most of our data at? Which means we need to leave 5% in our tails. Since our distribution is symmetric, we need like 2.5 in each tail. And we can find those percentiles, right, or quantiles that allow us to have that in each tail by using some NumPy functions. So there's a few different functions that you can use to do this. The first one I'm going to show is np.quantile. So it's the quantile function from the NumPy module. You give it the quantile that you want here. So for example, I could say I want the 0.5 quantile. Since I'm talking about quantiles, not percentiles, this is a proportion, right? This is as a decimal, so 0.5 would be like half. So this should show me where the middle of the distribution is. The other thing that I can do is use np.percentile. So if you use np.percentile, you need to give it as a percent right? Instead of as a proportion. So if I wanted to find that same middle part of our distribution, I could give 50 instead of 0.5, and you can see it gives me the same thing. So it doesn't matter if you use quantile or percentile, use the one that makes the most sense to you. To add even more confusion, Pandas also has a quantile function that you can use, and it works the same way as the NumPy quantile function, except instead of giving it an array, you can use .quantile as a method on a data frame. So if I make my data into a data frame, I can use .quantile. So you have options for arrays or for data frames here. I'm going to go ahead and just use np.percentile. And I'm going to find my lower bound here to use for my confidence interval by looking at this distribution. I'm looking at the distribution of Bootstrap statistics minus my original statistic, my Bootstrap parameter. And I want to find where only 2.5% is to the left of this particular cutoff. And it's giving me that happens around negative 145, okay? So somewhere in here, that makes sense. Then I can find the upper bound by doing the same thing, but I want to find where there's only 2.5% in this tail. So all the rest of the distribution is to the left. So I can look at 100% minus 2.5. That's going to give me my cutoff here. And it gives me about 153, which is right about in here. So these are the two cutoffs where 95% of the data is in the middle of these two percentiles. Now, our Bootstrap confidence interval equation is our point estimate, our statistic, minus this upper bound that we find here, and then our statistic minus the lower bound that we found. So I can calculate that right here and here, and I end up with my confidence interval being 530 to 829. So let's look back at our distribution here. So here's our distribution with our point estimate right here, about 683. And we're saying that our 95% confidence interval goes from 530 to, what was it, 829. So right about here. Now, you might notice that it seems like we probably could have gotten that same information if we just found percentiles on this distribution. Some people do that. They don't go through actually using this equation. They just get their Bootstrap statistics and find the appropriate percentiles of this distribution and use that as their confidence interval. That's called a percentile Bootstrap confidence interval. It's kind of like an approximation of our Bootstrap confidence interval, which is already an approximation because we're doing bootstrapping. So this confidence interval is a little bit more technically rigorous. A lot of times, especially when you have nice looking distributions, these are going to end up giving you extremely similar answers. So this is how you would use Python to actually create a Bootstrap confidence interval in practice. So we've gone from the theory of talking about how we would have done it to actually seeing how you can do it with some data. And this gives us more information, right? I can say now that if I created, let's say, 100 of these confidence intervals from different samples of penguins in Antarctica, I could say that about 95 of them would have the parameter within them. I don't know which 95, but I know 95 of them should include the parameter based on how we've created our confidence intervals. That is how we developed this equation, right? So 95% confidence interval means that 95% of intervals created like this will include the true parameter. So I don't know if mine is one of those 95%, but this is our 95% Bootstrap confidence interval. All right, so that's an example of how you would use Python to calculate a bootstrap confidence interval. I hope you enjoyed the video and learned something from it. If you did, please like it, leave a comment, and also subscribe to my channel. Check out some of my other videos. And if there's something you want to learn that isn't on my channel, let me know. Comment here on my video. I would love to make more content for you guys. Thanks for watching, and I'll see you in the next video. Bye.